too much time to talk about many different things. I only need 20 more minutes to cover the Newton's method for n equations and unknown, but since I couldn't do it, so your coverage is cut short. So it's good for you, isn't it? So, well, save it for final, right? you can escape it. Well, so we only covered item number 1 for the exam number 2 on Tuesday. Cover item number 1 to number 4. Okay, so the first topic is I want to talk about, just review the concept a little bit about is the cubic spine. Okay. It is it's not covered in the book in chapter 8, but cubic spine is very useful numerical techniques for interpolation, differentiation, and integration, especially when you have data points that are not evenly distributed. Okay, so you go to lab, take data at different times. Chances are you won't take exactly the data at 1 minute, 2 minutes, 3 minutes, or 4 minutes. Sometimes you take it at 1 minute. The next data point you collect may be 1.5. The next one may be 2.8 minutes, things like that, not evenly distributed. So you have all these data points with not evenly distributed in time, then then a lot of other data, other techniques may not be as accurate or efficient as the cubic spine. Okay, so let us say that I have so many data points here. Let me draw the data point first. I have collect data point, okay? So these are the data point 1, 2, 3, 4, 5. I have 5 data points. The idea of cubic spine is to do the following thing. So cubic spine is to use a cubic polynomial to join 2 points, okay? So let me just use this spine number 1, and then I'll use other color to do that. Now, Peter, today you sit at the front row, so you will be able to see all the color.
Oh, yeah.
Okay.
That was the plan.
All right. See, when you are living in a colorful world, it looks better. Right? This one needs to throw away. Okay, so I have different spine. Let us take this spine here. Okay, let me number 2, spine number 2 here. So so each of these is curve is a cubic polynomial, and it's a piece by piece. You have 5 data points here. You have, therefore, we have 4 cubic polynomial, or piecewise cubic polynomial. We call it cubic spine. So let me just say that for spine number I, for I spine, I have, let me use the book, use my notes notations so that I won't confuse you, okay? And let's say this is x, and this is xi plus a. this point here, these two data points. I think in my notes, I call it equation 1. So this is, yeah.
What is that letter? What is that letter at the start of the equation? Is it f of x or?
This one?
Yeah.
Oh, just call it S, okay? Spine. Cubic spine, right? You can call it function f. The book may not like it. Remember in Newton's method, chapter 3, our book probably is the only book that when it talks about Newton's method, they use R instead of function f. But it doesn't matter, just a function. Because it's a spine. Spine, call this spine number 1, spine number 2, spine number 3, spine number 4, right? So we are talking about spine number 2, so this is I equal to 2, right? Each spline, because it's a cubic polynomial, so it has 4 coefficients, okay? 4 coefficients. So that we talk about the idea about cubic spline, and that is in the interior points here between these two spines, for example, this one, not only the function is continuous between these spines and S1 and S2, that means the function evaluated by S1 will be the same as the function evaluated at this point by S2. We call it C0 continuous, right? Cubic spline is C0, C1 and C2 continuous, okay? I use this notation, C0, C1, and C2 continuous. So that means this is the function, and this is the first derivative, okay? 1 here means first derivative. C2 here means second derivative. They are continuous. Let's say at this point, that means at the point xi, if I use S1 to calculate its function, to calculate its first derivative and second derivative, it will be the same as the function, the first derivative and the second derivative calculated from the second spine at the same data point. Therefore, we call it C0, C1, C2 continuous. Okay, so it's pretty smooth kind of polynomial to fit the data. So all this, for each spline we have 4. For each spline we have 4 coefficients, right? And we are using these kind of condition to form an equation to allow us to calculate the coefficient pi1 to pi4. Okay. Now in this course, I did not get into the detail to write down all those equations to allow you to do that, because let's say in this case we have 5 data points, so we have 4 spines. So total, each spine has 4 coefficients. So I have 16 coefficients to evaluate, right? So I have to come up using this C0 condition, C1 and C2 condition to formulate those 16 part of the 16 equation, linear equation, to allow me to calculate the coefficient. So to to avoid the details of formulation, I basically tell you that we can use the following MATLAB. So this is XY data given to you, and then you form a structure called PP, and then you use the MATLAB command here called our goal is basically to get this guy, because once you get the coefficient, you will be able to do all the interpolation using that formula, equation 1. Yeah.
What's that first word in that bracket?
Oh, breakpoint. Go back to look at my notes on Canvas, okay? So this, behind these two commands, using these two commands, is basically to solve this 4 times n coefficient, unknown coefficient. In this case, n equal to 4. We have 4 cubic spline here, so total of 16. So these two commands, when I enter the point x and y, there are 5 data points here. It will formulate and set up those 16 equations and calculate all those coefficients. So all of these are contained here, okay? So basically, when you look at, after you use this, you will have, you can print out the coefficient here. This coefficient I and L, okay? I represents the I pieces, I spline, and L is from 1 to 4, okay? So L equal to 1 for I, this will be actually P1I, L equal to 2PI2, okay? So you get all these, this 16 coefficient here. Okay? So you can read from this table and plug into this equation 1. And you can do interpolation, and interpolation in this case means that for any value of x, right, that is within the lower bound and the upper bound of the data. So x is equal to this. That's called interpolation, right? So interpolation basically is a definition of the cubic spline for at the eyepieces of the eyepiece of the cubic spline. You use these two commands. Don't even memorize this, okay? I may give you a table of this or coefficient, and you, once you know how to calculate or extract the calculation, the result from MATLAB, from these two commands, you get all the coefficient you need. And then you can use equation 1 for interpolation. How about differentiation? dSi dx. You can differentiate that, right? That will be equal to pi what else? Pi 3, right? X is again at any point between between the lower bound and the upper bound. Right? That's called numerical differentiation, isn't it? Right? Integration, the same. That's your integration for the piece. That's the area under the green curve here. That's I2, right? I equal to 2. Make sense? So you can do all three things once you find equation 1 here, and you know how to use the cubic spline coefficient calculator from MATLAB, and then you can do interpolation, differentiation, and integration. Especially useful if your data are not evenly spaced out. Yeah.
So, when you said that when this was beyond the exam, you'd give us this table, and we wouldn't have to worry about the commands, you'd just give us the table that you were starting?
Yeah, I will just give you the table. Right? I may even give you equation 1. I give you everything. No need to memorize all these things, right? The concept is important. Once you know the concept, you say, oh, wow, it is a good thing to know that you have some useful tool in your toolbox to allow you to do numerical interpolation, differentiation, integration for any data point. All right? All right, so any question about that? In your homework, the homework problem, I think homework number 3, part B, and problem B2. You see the MATLAB program. In the MATLAB program, I think I have 7 data points. Okay, they are not evenly distributed. Now you can use trapezoidal rule to do that, right? You can draw a straight line instead of a cubic spline. You draw a straight line between a pair of points, and you can do integration by that trapezoidal rule. But remember, trapezoidal rule is piecewise linear, right? It's a piecewise linear polynomial between two, or straight line between, draw a straight line between 2 data points. A cubic spline is smoother. It's smooth, right? Cubic polynomial. So actually, for a lot of data, it turns out that cubic spline can do a better job than trapezoidal rule. Okay, you see the program there. All right, because of the time, let me move on to Gaussian elimination linear for linear system. Okay, in the lecture, I basically give you a linear system, 4 equations, 4 unknown problem. Okay, so let me generalize that a little bit, and that is Ax equal to B. Let's say this is n by m, n by n. This is n by n, and B also is n by n. Okay? Multiple right-hand side. M can be equal to 1. If m equal to 1, that B is nothing but a column vector, right? we go through the detailed example in the class. But m can be greater than 1. Okay? Remember in your homework that is due on Monday, I asked you to calculate the inverse of the matrix, right? Let's say for that case, if m equal to n, okay, first of all, if m equal to n and also B is equal to I, the identity matrix. This identity matrix basically is I, right? I is n by n because n equal to n. Then x will be the inverse of A, right? Because by definition, A times its inverse is equal to I, right? So in your homework, I ask you to basically find the inverse of the use Gaussian elimination with partial pivoting to calculate the inverse of A. Now that homework problem is a kind of a monster, isn't it? Because it's 5 by 5 matrix. It is not a monster, but it's not very friendly, right? Very tedious. So the idea is that some of you may struggle and to see that how do you calculate the inverse, okay? So let us how about this is the linear system with multiple right-hand side. When m greater than 1, we are talking about linear system with multiple right-hand side vector, column vector, right? There are m column vectors here. So in this case, for the to calculate the inverse of the matrix, in order to not just to know the mechanics, how to calculate the inverse, let us go back a little bit to the theory of this, okay? How do you, this is linear system written in matrix form, right? How about I write this for I row or I equation, okay? Remember in a matrix, the ith row actually represents the ith equation. That's what it means here, okay? The j column represents the j, represent the unknown, okay? So here, I can write that as A for ith row and j column. I can write this k is 1 to n equal to b I j for ith row, right? So this is the ith row equation. K is repeating index, repeating itself. So you can write this linear system in matrix form this way, or you can write this is component form. I call this component form, right? Because it's I and j. Because it's I and j. Now, it is actually, this is more compact and easy to do, right? Write it in matrix vector form for linear system is a common thing to do. But I want to tell you, if you understand that this, how to write the component form, actually is more useful and more explicit. This is more abstract, isn't it? But this is more explicit. Explicit in the sense that, hey, I am talking about this is the I equation for the J column, okay? For the J column. So I and J are actually fixed in this case, okay? So what does it tell me how I can use this idea to allow me to calculate X, okay? So in other words, if I fix J equal to 1, okay? Let's say if J equal to 1, what does it mean? This is A, I, K, X, K, J, J equal to 1, so J is fixed. So the above equation equal to this, right? If you look at this carefully, this is like A matrix times the first column of X equal to the first column of B, okay? So this is the first column of X. Now X is defined as this, obviously how many? M equal to N, right? So this is X1, X2, all the way to Xn. So this is the first column of X. This will be the N column of X. Does it make sense to you? As by the same token, B is B can be decomposed or written in this way. B1, B2, B3, Bn. This is the first column of B. This one will be the N column of B. All right? So this is actually you eventually use this concept to calculate the first column of X by backwards substitution later on, okay? So that is the idea. So now, if I go back to this problem, the homework problem, I have N equal to 5, right? So the idea to solve the problem, and we want to find how to calculate the inverse, this 5 by 5 inverse. Man, it is a monster. 5 by 5, you have 25 unknowns to calculate, right? So I'm asking you, well, you know, if you look at any matrix book, and if you are asked to calculate the inverse, the 5 by 5 matrix, inverse of a matrix A, which is 5 by 5, analytical by analytical formula, it is a monster. It is truly a monster. So we are using Gaussian elimination to help us to do the problem. So today, to calculate the inverse of any matrix, we just use kind of elimination techniques to do. Okay? So step number 1, you form the augmented matrix. Call it AA. AA is basically attach the I, the right hand side, or B, okay? A, I or B, since B equal to I, right? If I want to calculate the inverse of the matrix, so you attach the identity matrix on the right hand side. So this will become N by 2N, right? So this augmented matrix now is very, there are 2N columns and N rows. Now you do the Gaussian elimination from there. You can do Gaussian elimination in a naive way, straightforward way, that means without partial pivoting, or you can do it more sophisticated by partial pivoting, right? So that is what I asked you to do in the homework. Now you use step number 2. There will be there will be n minus 1 cycle, okay? They are performed, you are going to perform n minus 1 cycles of elimination, okay? So you perform the elimination of this exactly like what I did in the class. I did it one time for naive Gaussian elimination, that is Gaussian elimination without partial pivoting, and I also repeat the same problem for partial pivoting. All right? So now you do the role switching, the partial pivoting. Are there any questions about that? Switching the role. No question. Okay, everybody have it under the bell, right? Okay, so if you need to do role switching because in the homework you are asked to use Gaussian elimination with partial pivoting to find the inverse of the matrix. So you look for the largest absolute value under the column and choose it as a pivot element, and then you switch the role. Remember that is a concept, right? So ultimately, when you do the Gaussian elimination with partial pivoting, let's say partial pivoting, you get the answer like this. This matrix, after this n minus 1 cycle, you get this. Now, A is no longer a full matrix, and it's an n by n matrix, but it's an upper triangular matrix, okay? So this U, after the Gaussian elimination with partial pivoting, you get an upper triangular matrix. And I is the identity matrix, right? Very simple, just 1, 1, 1, 1, 1 at the diagonal. But after Gaussian elimination, it is no longer an identity matrix. I call it I prime, okay? Now, in order, the final step to calculate number 4, okay, the last step to calculate the inverse of the matrix or the X, okay, or the X over there. Let's say X is actually the inverse of the matrix, and X is written in this way. Okay? X is written in this way. So X is A minus 1. You have 5 columns of that, right? And then you have I here. You also split it into 5 columns. I1 prime, I2 prime, all the way to I5 prime. All right? Now, to calculate X1, which is the first column of X, or inverse of the matrix, right? So I calculate this U X1 equal to I1 prime, U X2 equal to I2 prime. These are all back calculation, back substitution. So how many are there? Because you have 5 columns, you do 5 backward substitution. The first back substitution, you get the first column of your inverse matrix. You do the second backward substitution using the second column of the transformed right hand side I. You get the second column of the inverse, and so on and so forth. Okay? So this is the way that how we take advantage of Gaussian elimination to solve a general AX equal to B problem or inverse problem. All right? A lot of, you can see that by hand, if you do it by hand, it's a lot of calculation. Oh, don't put it on the YouTube. I don't look so handsome, remember, please don't do that. All right, any question about that? How you calculate inverse, okay? We no longer use the old definition of theoretical calculation of inverse because that takes so much time to do that. So tedious to do that. We use Gaussian elimination to do our job, all right? Now, one final reminder. How do you calculate the determinant of a matrix? Now, if your matrix is 2 by 2, you don't need to do that. Every engineer know how to do that. Determinant of 2 by 2. If it is 3 by 3 matrix, some of you may struggle. 4 by 4, forget about it. Half of the class will make mistake, even though you claim that you know how to do, but it will make mistake, right? So, again, the modern way of calculating the determinant is by this formula. This will be the product of U11, U22, U33, all the way to UN. Okay? All these are the diagonal. These are the diagonal elements of U. So, since you already finished the Gaussian elimination, you have the upper triangular matrix, you obtain all the diagonal elements, you know what it is. And you just form the product. Okay? So the P here is the number of row switching